much. Okay, Jun, go ahead.
Yeah, okay, so, okay. Yeah, thank you very much for inviting me to this wonderful workshop. So today I'd like to talk about understanding embodied cognition through free energy minimization. So as Andy talks about free predict process in a rather philosophical way, I'd like to talk a little bit more technical things in using robot things. So, okay, so then I'm going to provide a brief review about the predicting the active inference. So, okay, so predict coding is actually theory for the perception, and then that try to minimizing the error between the top-down sensory prediction and its bottom-up outcome by inferencing or updating the latent states, internal states. On the other hand, active inference is a theory for the action generation, the minimizing the prediction error by changing the sensory inputs by adequately acting on the environment. However, important thing is that these two are not separated process, as action, perception make a loop through the environment. So maybe I'm going to show you a little bit more intuitive picture. My group have worked a relatively long time about analogous model to those framework, especially implementing those into the hierarchically organized recurrent neural network. So this is the higher level, slowly operated recurrent neural network connected to the middle level and the first level and lower level. This is fastly operated. So we may have this might be associated cortex, and this is kind of a proprioception branch, and this might be the vision branch. Then, so we might have the intention for intending to act next in the environment. Then that brings some kind of the predictive outcome sensation about the proprioception and the vision. Then actually in prediction of the proprioception means that the prediction of the next joint angle in case of the robot. That one is fed into the PID controller. The motor torque is generated, acting on the environment, and the state change occurs. Then we're going to have a proprioception and the vision sensation. Then if we have the error between the prediction, then this error once is going to fed into the PID controller and regulating the motor. And the other is that the further this goes up, bottom up, in a both channel to the associated cortex, and then try to change the intention for minimizing the prediction error. So therefore, we have this one is kind of a changing the internal state by the predict coding. The other is changing the word by active inference. These two things occur simultaneously through the bottom-up, top-down interaction. So then, however, we have worked on a kind of deterministic model, deterministic recurrent neural network model, and cannot treat well about the probabilistic phenomena. So then, the question is that are there any way to bridge the gap between deterministic models and the probabilistic model? Then answer might be the free energy minimization. So okay. So then based on this thinking, so we developed something called PVRNN, that is a variational based recurrent neural network. And then that is try to minimizing free energy represented by the accuracy term, that's prediction error, and the complexity term has to be minimized, weighted by the something W, that's meta prior. This value have to be minimized. Summation of these have to be minimized. Then I might talk a little bit about the architecture, and especially explaining about the scheme of the online prediction with the inference of the past based on prior learning. So this is a time development. So the step goes this way. This is random latent variable. And this actually forms something called sequence Gaussian prior. So that each step we have a prior estimation of the prior we're going to have that change in time. Then that one is fed into the deterministic latent variable D each time step. Then it's going to generate prediction of sensation, perception, vision at each time step. And then we have a actual sensation comes, observation comes, and we have the error here. Error is propagating, back propagating, then updating the posterior. That's the posterior inference comes. The important things here is that we have to minimize both error here, accuracy term, and the complex, and then KL divergence between the posterior and the prior. That's a minimizing complexity term. So that one has to be done. Then that is by minimizing free energy in this manner, then latent state is situated to the sensory sequence. Once network is situated to the sensory sequence, then you can predict next things, prior prediction comes. Maybe we look at the hierarchical organization, we have, this is a higher level, the lower level, and we have a top-down prediction intention flow comes along the time. Then we have a perceptual reality, sensation comes, and the error is bottom up. And we're gonna update the posterior each time step for the each layer. Once network is situated, then you can predict the next one. Then this inference is kind of a cycling many iteration. Then once minimized, then it goes to next time steps. Time is shifted. So this continues in this way. So then we did a lot of robot learning experiments, and we found that different type of structure get self-organized depending on the setting of the W during the learning, metaprior W. Then what we found is that, so metaprior is coming here. And what we found is that, so this is a fracture temporal pattern experienced that when we set W is larger, and then this pattern is embedded in a deterministic chaos. And on the other hand, W set small, it's going to be reconstructed in a stochastic process. So then it means that when the W set is larger, high precision prior is developed. This means that a strong top-down belief comes out. That means that a strong sense of the agency comes. That means that the strong congruence between what is intended and its perception outcome. So if we set W small, the other way around is coming. So now we look at the robotic experiments. Okay, so this is a humanoid robot in have a force feedback controls, and then now is generated spontaneous behavior based on prior learning. The handler is interacting with the robot physically, and then he can sense the intentional robot through his hand because through the pushing the pulling. This robot trained with a high W metaprior. This robot is trained with a low W. So then it's more difficult to manipulate this robot in this case, but this case more easy, robot is flexible. When we set the metaprior W intermediate value, and a very good mutual interaction between handling robot take place, you see the good synchronization between. So now this person is a tutoring robot by physically guiding the robot by feeding the intention of the robot. So that's kind of a interactive way of tutoring the robot. So now these two robots are imitating each other. This robot is set with a high W. This robot is set with a low W. Therefore, this robot is leading this robot. You see that this robot is predicting stably and agree with the outcome. So in the post-prediction, but this robot is more in a set W small and the prediction is unstable, and that prediction is betrayed in the actual outcome. So now it's coming to the end almost. So then when we set the robot in the W with a larger value, what we see is that so high precision prior developed. Therefore, posterior was follow this intention, ignoring sensation from the human. Therefore, the robot is going to more dominating the human. On the other hand, if we set the robot small w for the robot, the low precision prior comes. Therefore, posterior is followed sensation, ignoring the own intentions. Therefore, it goes to the robots dominated by the human. So the point is that so we can feel the intention of the robots in our hands by means of embodied interaction through the FEP, free energy principle implementation. So the future study should examine how the meta prior W can be self-determined through the experience. So thank you very much. That is the end of my talk today.
All right, wonderful, Jun. Thank you very much. It's a perfect 10 minutes presentation.